I'll start. Okay, welcome to today's lecture. So today we'll do a deeper study of smooth Renyi divergences, which had started last time. So, okay. So previously we had seen that the Renyi divergence satisfies data crossing inequality. So this is true for any alpha. And then we had defined the smooth Renyi divergence. So recall, this is the definition of smooth Renyi divergence. So I prefer not to do smoothing for alpha equal to 1. So if you at all want to do, you'll have to take a minimum, but as it will become clearer today, it is nicest when I don't bother about alpha equal to 1. That's a really special case. That is a good old Shannon relative input. So today's lecture, and as we go ahead in the next lectures, we will see the very special position of D1. So we'll not smooth D1, but we'll smooth everything else. So for alpha larger than 1, the smoothing will take a minimum. So it's minimum over P prime, which is below P, but the difference between P and P prime is not so much. It's only epsilon. So epsilon is the smoothing parameter. And now I'll evaluate the alpha Renyi divergence for P prime with respect to P. Note that Q is not disturbed in the smoothing. It's only P that is disturbed. Similarly out here, but here I maximize in the epsilon ball around P. And I was just telling Ishan, at least by looking at the extreme example of D0, that maximization is a sensible thing to do for alpha less than 1. Okay, at least for alpha equal to 0, that's a sensible thing to do. And for infinity also, one can give a similar logic that minimization is a sensible thing to do. So why min and max, it will become much clearer in a few slides. So as we understand these quantities. So recall d epsilon max. So has this nice characterization. So d epsilon max is another word for d epsilon infinity. So we were just discussing this. So it is the minimum over thresholds lambda such that this quantity is less than epsilon. So remember this notation in flowery brackets, p minus 2 to the lambda q with a subscript of plus means those sample points x where the ratio of px by qx is larger than 2 to the power lambda. Or in other words, if I do this difference, px minus 2 to the lambda qx, this is greater than equal to 0. That's the plus ID. And the idea being that without smoothing, d infinity was just the maximum ratio of px over qx. Now this ratio can be unnaturally large because of some pesky culprits x, which overall don't add up to much even for p. So there are these culprits x whose probability mass under p is less than epsilon, but whose probability mass under q is much lower than that, so that the ratio is unnaturally large. So what I'll do is that for those pesky x's, I will lower p down to 2 to the lambda times qx. So that is the definition of p prime. So p prime is the same as p, except in this plus set, p prime x is defined to be 2 to the lambda times qx. And I want to say that the difference between p and p prime is not much. So this is basically the difference between p and p prime. Okay? So for x's which are outside this plus set, p is equal to p prime. So this difference, this will not contribute anything to the total variation distance. For these pesky x's which have to be lowered, these are the ones which contribute to total variation distance, and this is the expression. And recall that d0, of course, was the log of the probability of the support of p under q. And if I want to smooth, the idea is I will throw away some excess from the support of p, okay, which will totally add up to less than epsilon for p. So S is the complement of the those x's that I've thrown away. So the probability of S under p is larger than 1 minus. Hello, somebody.
Sorry, sir.
So the probability of S under p is larger than 1 minus epsilon. And now I just want to know what is the probability of S under Q, that is this quantity, and then I take the negative log. I minimize over all such subgroups. Okay. So this is just following from the definition. And we also argued that d epsilon max is continuous in the parameters epsilon, p, and q, and satisfies data processing inequality. But the last thing that we saw is that d epsilon 0 is not continuous in epsilon. Okay, so that was this slide where we had stopped. So this is because as I'm increasing epsilon, see, as I'm increasing epsilon, I'm dropping more things from the support of P. So the set S is shrinking. S is the complement of the support, so that is shrinking. So this means that the probability of S under Q should go down, but there can be discontinuous jump. Like as I lose a point from the support, as I lose a point from S, the probability QS can have a discontinuous non-zero jump downward. So that is the source of the discontinuity in B0 epsilon. I want to remove that. Okay. Just a sec. Okay. So this is not continuous, and we'll remedy in the next slide. But note that D0 was always greater than or equal to 0, and the smoothing is the maximum out here. So D0 epsilon is greater than or equal to 0. So this is a good property of D0 epsilon. And it's unfortunately D epsilon max can be negative, which we had also argued last time. And this usually happens when P is very close to Q and epsilon is larger than the L1 distance between P and Q. So any questions? Okay. Okay, so let's go ahead. Okay, so let us try to do something about D0 epsilon. Okay, remedy is discontinuity. So what we will do is that we will modify the definition of D0 epsilon. So this will give us d min epsilon out here. Okay, there should be epsilon out here. So to define d min epsilon, let's use some more notation. So 0x and 1x denote the all zeros and all ones x tuple. And now d epsilon min is defined by a linear program. It's also called the hypothesis testing relative entropy. So we
X tuple is this X is the set of all symbols.
X is the X is the sample space, the set of all symbols. Yes.
Okay.
So it's that X. Okay. So the it's also called the hypothesis testing relative entropy. This is the, and we'll justify this nomenclature. Okay. So this is the definition. Let's look at it slowly. So here I'm minimizing over the choice of all m's. Okay, so m is an x tuple, and m lies between 0 and 1. That means all the coordinates of m are greater than or equal to 0 and less than or equal to 1. This is what it means. So this is a linear constraint on m, on the vector m. There's another linear constraint which says that the dot product of m with p, okay, is greater than or equal to 1 minus epsilon. Okay, and the objective function is also a linear function. I want to minimize m dot q subject to these constraints. So one linear constraint is on m dot p, and two other linear constraints are on m of p. Okay. So this is a linear program, a minimizing linear program, and then I compute the optimum value and then take negative log and all. Okay. So as you can see, m dot q, the way I've defined it, m dot q is always less than or equal to 1, right? I mean, each coordinate mx is less than or equal to 1. So even if m is the all ones vector, m dot q will be exactly equal to 1, and then this will evaluate to 0, or else m dot q will be less than 1, and this will evaluate to something strictly positive. Okay. So one good thing, whatever this quantity is, it is always positive. Okay. So how to make sense of this? So this should remind you of our converse argument for noiseless source coding, the one-shot noiseless source coding. So informally, MX is a private coin algorithm that accepts symbol X with probability MX. Okay? So for every X, the private coin algorithm accepts X with probability MX. So it's a quantity between 0 and 1. Okay. So we can call this as my hypothesis test. Okay, this private coin algorithm is my hypothesis test. This hypothesis test should accept the distribution P with probability at least 1 minus epsilon. That is m dot P. Okay, and it should accept the imposter probability distribution. Okay, which is given by m dot Q with as low probability as possible. So this is basically the asymmetric notion of indistinguishability that I talked of. Okay. So this is the asymmetric smooth hypothesis testing divergence. Okay, this problem is exactly hypothesis testing. The ideal hypothesis is accepted with probability 1 minus epsilon. Okay, let's say epsilon is a small constant, so it's something like 0.99 out here. and it should accept the imposter hypothesis with as low probability as possible. So I want this typically to be exponentially small. Okay. So asymmetric because the threshold here is only a constant near 1 and the threshold here is typically exponentially small. Okay, so this is the definition. And now you can check that d epsilon mean is continuous in its parameters epsilon, p, and q. Okay, that's because I mean it's given by linear program, and if I let's say vary epsilon slightly, you can see that this feasibility constraint varies only slightly. So whatever was feasible later, okay, was feasible earlier. What was feasible earlier is almost feasible later, and these are all like smooth functions. So so whatever m was feasible earlier, that can also be applied for the objective function second case, and that will only cause a slight perturbation in the value of the objective.
I have a question. So take any LP, okay, any finite LP, and suppose that I kind of perturb the constant matrix A, let's say A, with some small perturbation, even along the diagonal, let's say, and I add suppose the identity matrix with all diagonal entries epsilon. Okay, is it true that the solution of the LP that changes continuously in this epsilon?
Yes.
Okay.
Yeah. I mean, if you define things properly, it's good. So yeah. So this is a fairly general phenomenon. Okay, and similarly, you can argue for P and Q. Okay. Okay. So I mean, you actually have to argue for the triple epsilon PQ, but I mean, you can extend that. It's a small exercise in real analysis. So this is a continuous thing, very nice, and it also satisfies the data processing inequality. So let me justify that. Okay.
So I didn't get this informally MX is a private kernel algorithm part. So what we have done is this definition d epsilon min, whatever we had defined previously, we have just kind of written it as this sort of a, we have rewritten it in some other way. Yeah, so the informally that part, like now what?
Okay, so let us say I increase epsilon to epsilon prime.
Okay.
So whatever is feasible for epsilon prime is feasible for epsilon. Feasible just means this success probability criteria.
Yes.
Okay, right? Now, so first of all, this says that if I increase epsilon to epsilon prime, more things may become feasible, so the minimum can go even lower. In other words, if epsilon increases, d epsilon min also increases. Okay.
Yes.
Yeah.
Oh, Pranav, I think the question was that what is the private kernel algorithm corresponding to M? I think that was the question.
Was
or
that
am I
the
wrong?
question? No, that was not the. I thought the continuity is the question. So let's try to prove that.
Okay.
Okay.
Yeah.
So let's take a M which is feasible for the second case with epsilon prime. Okay. Yeah. So it may not be feasible with respect to the first case, but the point is, I mean, epsilon prime is close to epsilon. Okay. So so let us say M prime is feasible with respect to epsilon prime. Okay. So let me write this. So prime. Okay, so this is what I was trying to say. So if you increase epsilon to epsilon prime, so the optimum of course increases because the feasible region gets bigger. But the point is that the new optimum is close to the earlier optimum. Okay. This is because any m, okay, any m prime which satisfies m prime dot p is larger than 1 minus epsilon prime, okay, is close to a vector m which satisfies m dot p is larger than or equal to 1 minus epsilon. Okay.
It's not very clear. I'm
Yeah.
still confused.
Yeah. So.
So can I say something?
Maybe go.
Maybe
Okay. Yeah.
I
Sure.
can help.
Yeah.
So basically, Ishan, the thing that is being said here is that suppose you have two vectors m and m prime. Okay? You take a common vector p, okay, such that the inner product of m with p is greater than 1 minus epsilon, and the inner product with m prime with p is greater than 1 minus epsilon prime. Epsilon prime is slightly larger. Now think of it in terms of geometry. Okay, you draw these three vectors on a piece of paper. So first of all, the first statement that the inner product of m and p is greater than 1 minus epsilon, that means that the angle between m and p is very small. Okay, m and p are almost aligned. But this also applies for the second guy. So what is being said is the second guy is like 1 minus epsilon prime, which is slightly larger. So that angle is also small. Okay. So now if you draw the picture, you will see that the maximum angle between m and m prime can be at most twice of the angle between m and p. Okay. So that means m and m prime are themselves also close. That's the picture.
Okay.
Yeah, I mean, that's all I had to say.
Okay. Yeah.
So just to be sure, like here m is just like a 0, 1 vector on the support of x, right?
0, 1 means each coordinate is between 0 and 1.
It's between 0. Okay,
between
but
yeah.
Yes. Yeah.
Okay. It's so maybe you thought earlier that each coordinate is either 0 or 1. No, each coordinate is between 0 and 1.
So
okay,
I mean,
so
in the
that
original,
is important.
Okay. Yeah.
That is important for the continuity.
Right. So right. Okay. So d epsilon 0, the one which we defined d epsilon 0, that in that it was basically m were actually either 0 or 1, right? The one which we defined above.
Yes.
Okay.
So that is either 0 or 1, and that is precisely why it was discontinued.
Right. Okay.
Good point. Yeah. So we make it continuous by making allowing each coordinate to vary continuously from 0 to
1.
Okay. So now even if you increase epsilon to epsilon prime, see that d0 epsilon was discontinuous because this slight increase of epsilon to epsilon prime allowed one more point in the support to come in. Right. Okay. And for d0 epsilon, if I'm thinking of in terms of n, bringing in one more point in the support means mx is jumping from 0 to 1. Okay, but if I'm talking of d epsilon h, then there is no jump. So sure, when the error was epsilon, m of this x naught was 0. But when the error increased to epsilon prime, m of x naught will be slightly above 0. It will not jump all the way. So that's another way to reconcile with d0 epsilon being discontinued.
And now, okay, so now this is like a new quantity which we are defining.
Yes.
And now when we say that mx is a private algorithm, like what is the goal of this algorithm? It is to
it gives a Boolean outcome, accept or reject.
Accept with probability 1 minus epsilon if
no, accept with probability mx.
Sorry, right. Okay.
It is given a symbol x. Okay.
Yeah.
So and it accepts it with probability mx. So in this part of the definition, this has nothing to do with p nor with q.
Okay.
This is just the behavior of the algorithm.
Okay.
So m dot p says that this algorithm will accept p with probability 1 minus epsilon. Okay.
So it's like
so the
in
okay, let me finish. The earlier picture of D0 epsilon was that algorithm accepts every x in the set S with probability 1, and it accepts every S in the set S complement with probability 0. Okay, but I'm relaxing that. I'm allowing your algorithm to accept a symbol X with an intermediate probability also.
So is this sort of this what you can call, like, say, hypothesis testing given a single observation, like
Yes.
that's
So this is the good old hypothesis problem. This is the one-shot hypothesis testing. Okay, and this is precisely the best that you can do in one shot. If you want to do asymmetric hypothesis testing, accept the ideal one with probability 1 minus epsilon, and accept the imposter with as low probability as possible. So this is precisely the thing you can do. The most general thing you can do is a private kernel algorithm. Okay, so a private kernel algorithm gives an outcome which is modeled by this. Okay, and it just becomes a linear program.
Okay.
So I mean, it is reminiscent of the converse proof of Shannon's noiseless channel coding. Just a second, to take this call. Okay, sorry about that. Yeah. Yeah, Ishan.
Yeah, I got it.
Yeah. Any question? So this is a new quantity, and we should understand this properly because this will be one of the two fundamental quantities that we deal with in the course. Okay. So this is I mean as the yeah. So the way to remember it, this is in fact the perfect characterization of asymmetric hypothesis testing. One shot. Okay, D epsilon H. Okay, and to convince yourself, maybe to get a better idea of why this is continuous, whereas D0 epsilon is discontinuous. So think of what happens when a new element just creeps into S. What happens for D0 epsilon and what happens for DH epsilon.
So yeah, I don't recall the asymptotic setting properly, but is it like there's something called the Chernoff-Stein lemma or something like?
They will all come. Don't worry.
So this is the analogous for one shot. And so that also was an asymmetric.
Yeah. So hold your horses. Maybe by the end of this lecture, you will have a better understanding. And yeah, we will look at the asymptotic IID limits now.
Okay.
Yes. So this will clean up what you may have heard earlier. Yeah. Further questions? If not, let's go ahead. Okay. Yeah. So these are the my two workhorse quantities, D epsilon max and D epsilon min. Okay. Now let me define a few more technical divergences. So what I'll define a new quantity called D epsilon S. So here the S is a reminder of something called information spectrum. So in the first lecture, I said there is another setting called the asymptotic non-IID setting, which is also known as the information spectrum setting pioneered by Hahn. So of course, in that setting, there is a n and the parameter n keeps growing and you have to
Pranab, I have a question.
You have a question? Okay.
Yes. So is it true that, I mean, we know that the best hypothesis test in any setting, so single shot or many samples is going to be this MLE, right? The maximum likelihood, and that can be proved by other statistical considerations, Lemur, Pearson lemma, etc. So does the LP always give? I mean, it should, right? It should always give the maximum likelihood test as the best algorithm, right?
See, the maximum likelihood test is D0 epsilon.
Is D0 maximum?
Okay, so it's not the best test. The point is that those guys quickly go to the asymptotic IID limit where all of them become the same.
Oh,
Okay?
I see.
So I'm telling you, all this Chernoff-Stein and all that, they quickly go to the asymptotic IID limit and they don't bother chasing epsilon deltas for the one-shot case. So we are going to rewrite the book.
Okay.
So the maximum likelihood is D0 epsilon in our language, okay, which is not as good as DH epsilon. But yes, if you go to asymptotic IID limits, they start looking more and more similar. In fact, I mean,
there to the flattening of the distributions happen because of Chernoff-Stein and all that.
Yeah. I mean, then in the extreme case, everything becomes D1, the Shannon relative entropy.
Right.
Okay, so yeah. So all these things will become clear. We will have precise upper and lower bounds on the epsilons and the n's and all that as the course proceeds. Just a few slides later on, we will visit this in more detail. I mean, a little more of hypothesis testing and the ratio of px by qx, which you like to call the likelihood. Okay, yeah. So I will now define another quantity called d epsilon s. So this s is for the information spectrum. So actually, if you look at the information spectrum books or the papers, so again, there is a parameter n which keeps growing, and then you have to define a certain quantity, take negative log or something, divide by n and take limits. Okay. So, but this is the one-shot case. You see there is no n out here. So actually, this definition is inspired from the information spectrum, but we are really taking the information spectrum definition when n is equal to 1. Okay. So yeah, so that's why in reference to Han, we are calling it S, but actually you will not see this definition exactly in that body of work because there will be n things will divide by n. But if you put n equal to 1, this is essentially what we draw. Okay, so let us see what, how is this motivated from our perspective. Okay, so in order to design a private coin hypothesis test that accepts P with probability at least 1 minus epsilon, but accepts Q with as low probability as possible, we can try this following strategy. So this is closer to the maximum likelihood strategy that Shayantan just suggested. Okay. So what we will do is we will arrange the symbols X in the ascending order of Px by Qx and discard as much of the head as possible. Head is those X's where the ratio Px by Qx is large, too large. So we will discard as much of the head as possible so that the set S of the remaining X has probability at least 1 minus epsilon under P. Okay. So this leads to this definition. So the head is precisely this, which we had just defined, P minus 2 to the lambda Q flowery brackets plus. So basically this is where the ratio is of Px by Qx is larger than 2 to the power lambda. So lambda is some threshold that we have set. If the ratio is larger, those are the bad guys. This is the head that I want to throw away. And the remaining guys which are not thrown away. Okay. So
this is ulta, right? The definition you have written should be less.
Yeah. No.
Minus.
No. So this definition is correct. So yeah, so I should say discard as much of the tail as possible. Okay. So this should be the tail. I'll correct it in the slide. This definition is correct. I was trying to write that in English and I think I got confused with tail over here. Okay. So the idea is I'll fix a threshold and my good set is those x's such that the ratio px by qx is larger than 2 to the power lambda. Okay. So now the probability of this good x's under p should be larger than 1 minus epsilon. Okay. Now, of course, if I increase lambda, so let us justify the maximum. If I increase lambda, then this set of good x's shrinks. Okay, so if this shrinks, then the probability under px will also shrink. So at some point of time, it will go below 1 minus epsilon. Okay, so the maximum lambda that I can tolerate such that this is larger than 1 minus epsilon. This is the definition of the information spectrum divergence. Okay. So actually, maybe I should also, if you see Han's work, I should also put it in the slides. So this is the quantity which Han calls something like Well, he doesn't always talk with P. So I think the original works he calls that I because he's in the mutual information framework. Okay. And so it's I with the bar below. So he's a mutual information framework, but we know more general than mutual information is the divergence. So you can define the same thing for divergence, set n equal to 1, and then you come up with this definition. Okay. Yeah. So this is like the maximum likelihood philosophy. Okay, well, I've set a threshold, my likelihood threshold lambda, and I've defined the good set. Okay. So why is this somewhat of a good idea? So of course I know that for the symbols in this plus set, their probability under P is larger than 1 minus epsilon. So if my hypothesis test is just accept the symbols in the plus set, then I'm done. This hypothesis test works for P with probability 1 minus epsilon. What about Q? Okay. So note that for this good set, the ratio Px by Qx is larger than 2 to the power lambda. Okay. In other words, Qx is less than 2 to the power lambda, 2 to the power minus lambda times P. So let me write that out here. So this is okay. So for x's in this plus set, Qx is less than 2 to the power minus lambda times Px. Okay. So in other words, the probability of this plus set under Q can be at most 2 to the power minus lambda, right? I mean, the probability of this P is, even if it is 1, the probability of this Q is less than 2 to the power minus lambda. So this looks like a good idea. So choosing this plus set as my hypothesis test sounds like a good idea because it's accepting P with probability 1 minus epsilon and it's accepting Q with probability at most 2 to the power minus lambda. Is this clear to everybody? Okay. So that's the motivation for this definition. But unfortunately, you can see that d epsilon s is not continuous in epsilon. And this is for the same reason. So if I increase epsilon slightly, okay, that means I'm lowering my threshold for P out here. In other words,
So suddenly an extra P can come
yeah,
in and
in other words, I'm allowing you to enlarge the plus set. Then suddenly an extra x naught enters the plus set. Okay. And because an extra x naught enters the plus set, that causes a sudden jump in the probability, whatever, that causes a sudden jump in the threshold lambda out. Remember, I mean, lambda is just the borderline threshold. So if something new comes in, that causes a sudden jump in lambda. So this is not continuous.
Is this not equivalent to the D0 definition? Because there you were, your witness was a set, here your witness is some lambda,
No,
but is it not the same thing?
No. They are kind of related. I mean, the D0S optimizes over all subsets. Okay.
Oh,
Whereas
okay.
this
Oh, you're not
prescribes what the
setting
subset is.
okay, I see.
Okay, so this is less than D0. Yes. Okay, so that will become clear. I mean, I'll write it formally in the next slide, but this is less than D0 because D0 is allowing you to optimize over all subsets. Here, Han is prescribing what subset to use.
Okay, got it.
Is that clear? Okay, let's go to the next slide. Okay. So this was my information spectrum divergence. Okay, but it is not continuous. So let's try to remediate. So to remediate, we'll take a leaf out from the Dmax epsilon definition. Okay, and why is that? Because the reason this was not continuous is because an x naught suddenly creeps into this plus set, and that causes a discontinuous jump in lambda. So we'll try to smooth things out. So what I'll do is that for this objective function instead of P, I'll replace it by Px minus 2 to the lambda Qx. Okay, and I'll call it D underbar epsilon s. Now the claim is this is continuous. Now why is this? Let us say I start decreasing epsilon. So this threshold is going lower. That means more excess can creep into the plus set out here, right? More terms can creep in. But let us say a new x naught has crept into this plus set. What will be the contribution of new x naught? Okay, the contribution of the new x naught here will be 0, because when it just creeps in, px naught is exactly equal to 2 to the lambda qx. Okay, in other words, this lambda has gone down continuously. So as epsilon increased continuously to epsilon prime, lambda was also going down continuously. Okay, so that eventually when things creep in, lambda is at the right threshold, so that this contribution for the new x naught is still 0. Is that clear?
Can you repeat that once, please?
Yeah. Okay, so let's look at d epsilon s. Let me try again. So I have fixed some lambda out here. Okay? So this lambda has fixed the plus set, right? And the probability of the x's in the plus set is larger than 1 minus epsilon. Now let us say I am increasing epsilon, so lowering the threshold. Initially nothing happens because if I have to put in the next guy out. So what is the next guy? Next guy is this x naught, such that so let me draw a figure. Next guy is this x naught. So this is x naught. And what is the thing? Okay, so this is what I mean by the threshold. So let us say lambda is the optimal solution that I have for d epsilon s, and then x naught is the next one. Okay, so x naught is the guy whose ratio, whose likelihood is below 2 to the power lambda, but it's just below 2 to the power lambda. Like the other x's have even lower ratios. Okay, so this is the next candidate, so to speak. Now, for what will happen for d epsilon s is as epsilon increases to epsilon prime. So okay. So what does this mean? So as epsilon increases to epsilon prime, at some point x naught enters the plus set. X naught enters the plus set means, what is the plus set? So okay, so x naught enters the plus set means even when I add the probability of x naught to whatever probability I had earlier, it will be greater than or equal to 1 minus epsilon prime. Right? So I increased epsilon to epsilon prime. So 1 minus epsilon prime is a lower threshold. So I can afford at some point to add one more point x naught into it. Okay. But the moment I add x naught, the smallest ratio will now be determined by x naught. So now, so let me write that. So let me, what is lambda? Okay. So let's give a name to the ratio px naught by q. So that is 2 to the power lambda prime, which is less than 2 to the power lambda. So as epsilon increases to epsilon prime, at some point x naught will enter the plus set. That is because even after adding x naught, the probability out here is larger than 1 minus epsilon prime. Okay. But the moment epsilon enters the plus set, there's a discontinuous drop of lambda to lambda prime, because the smallest ratio of the likelihood is now determined by x0, which is 2 to the lambda. So is this part clear? Why there's a discontinuous drop in d epsilon s? Yeah. But let us see what happens to d lower bar epsilon s. Okay. So I start off with epsilon and I start increasing it slowly. As I increase it slowly, I can afford to increase this lambda. Okay. So let me write. So what is happening is this. Okay. So for the underbar definitions, let's write. Okay. So for the underbar d epsilon s definition, as I increase epsilon to some epsilon double prime, which is let's say less than this dangerous epsilon prime. Okay. So for d epsilon, there's nothing happened because the support, this plus set was not changed. But in d lower bar s, fine, the plus set doesn't change, but I can afford to increase lambda to lambda prime and still keep this larger than 1 minus epsilon double. So actually, lambda does decrease to lambda prime. Okay. And then as epsilon double prime is increasing and hits epsilon prime, similarly, lambda double prime decreases and hits lambda prime. And nothing bad happens because fine, I'm at lambda prime out here. The plus set has gone up. X0 has crept into the plus set, but the contribution of x0 now is 0 out here. So this is exactly 1 minus epsilon. So there's a continuous smooth variation. So is this clearer now?
Yeah, it's clear to me. I don't know about Ishan.
Yeah.
I'll look at it again like once.
Okay. Yeah. Go and think about it. Yeah. Fine.
Basically, the extra thing that happened is previously I had no control over the mass on this set, but now, therefore,
Well,
previously what
it's not the mass. It is this objective function.
yeah, this objective function exactly. So now what I'm doing is, as I'm increasing epsilon, I can parallelly increase lambda also even before the thing, even before x0 creeps in.
Correct.
So as I'm changing epsilon, just by changing lambda, I can keep the objective function the same. That's the thing. And
yeah,
the moment epsilon,
you can keep it saturated. See, for
you can keep it saturated exactly.
Another,
so the moment,
yeah. So Shan, then let me just say, then you can continue. So one thing to note out here is in d epsilon s, often this inequality will be strict. This will not be saturated. This is because let us say epsilon increases to some epsilon double prime. For d epsilon s, what happens? I cannot bring in another point into the support because then this summation shoots up by a I mean, non-trivial jump. So I cannot bring anything in. Okay, but yeah, but now what am I saying? Yeah, but then yeah, but then what I can do is I can, for example, yeah, okay, so it is saturated, but so what I was trying to say is not correct. But anyway, Shantan, back to you. The point I was trying to make, and Shantan was also saying, is the for d epsilon s, as you increase epsilon, like you are stuck with the same lambda because the support is not changing. Okay, and at some point of time when a new x naught creeps into this plus support, then you are forced to drop lambda to lambda prime. I mean, it's a sudden jump downwards. Okay, but what happens in the lower bar is, as epsilon increases, you can afford to bring this lambda down. Okay, whereas in d epsilon s, you cannot afford to bring in this lambda down because it is just px out here. Okay, and summation of this pxs is exactly equal to 1 minus epsilon. So you cannot afford to change it. But here, the px part is the same, but you can afford to increase lambda out here, even though the qx is the same. The plus set still remains the same. X0 has not crept in. So px, qx are the same, but you can afford to increase lambda slightly while preserving this inequality with epsilon double prime. Okay, so you can smoothly track the decrease epsilon double prime here by lambda double prime. Yeah, Shantan, back to you.
So you pretty much said what I was going to say. I mean, the entire trick in proving all these continuity results seems to be saying that you have to keep the objective function saturated. That's the whole game here.
Yeah, you have to keep it saturated, and yeah, I mean, basically we saw like things that depend upon choice of subsets. Okay, hypothesis test which depends on choice of subset, or this plus definition which is just a subset. Okay, so these are discrete quantities, so this will damage continuity. Okay, so in the d-min case, what we did was we smoothed the subset, like we made the feasible, we changed the definition of feasible region by this. Okay, an alternative thing which you can do is that you don't smooth the subset remains subset, but you change the objective function. So the objective function becomes non-linear. Okay, out here, but that's fine. Well, it's non-linear because I'm talking of lambda, or else it's still linear. But I mean, if you are trying to optimize 2 to the lambda, I mean, I can always say I want to maximize 2 to the lambda, then the objective function is linear. But yes, so yeah, you can smooth it by changing the objective function. I mean, if the objective function only depends upon your discrete subset, then you're in trouble like this. But if your objective function has some extra degrees of freedom, like extra parameters, then maybe you can smooth things out. So that's another takeaway. Okay, so further comments? Okay, if not, let's proceed. So yeah, so recall this was d epsilon max, and this was d epsilon min, which you just defined. But now observe the following. Okay, Shayantan just said, like, I mean, it is important to keep these quantities saturated. Okay, which which was not the case here. Like when epsilon decreased to epsilon double prime, the left-hand side still remained the same as before, 1 minus epsilon, but the right-hand side became 1 minus epsilon double prime. Whereas here it was saturated. Okay, this was always equality, right? Out here, because the lambda was decreasing to lambda double prime. So now observe that the optimizing distribution in the above 3 definitions satisfy the feasibility conditions with equality. Like here, as well as here. In these 3 definitions, okay, the feasibility constraint is always saturated. Now this implies that d lower bar epsilon s is basically D max with epsilon replaced by 1 minus epsilon. So look at these two definitions. They're just the same thing. Okay. But yeah, to formally assert that these two are the same, you need the equality. Okay. I mean, just inequality would not have worked. I mean, if it was inequality, it's possible that the optimizer here is strictly less than epsilon, and the optimizer here is strictly larger than 1 minus epsilon. So I would not have been able to say it. But the point is, I know whatever the value of epsilon is, the optimizer here satisfies this equality, and same here. Okay. So, okay, so once we observe this, we realize that D lower bar epsilon s satisfies the data processing inequality because D max 1 minus epsilon satisfies data processing. So is this clear?
Yeah.
Yeah. Okay. Good. Yeah. So let us collect all the quantities that you defined. So there was D epsilon min defined by the LP, D epsilon 0, which is maximum likelihood. Okay. Then there was D epsilon S, which is Hans prescription for maximum likelihood information spectrum. And then we smoothed it to D lower bar epsilon. Like this. Okay. So now the theorem is that all these four quantities are roughly equal. Okay. So more formally, I have this chain of inequalities. So let us see. The last three inequalities are trivial. Okay, so last three inequalities are this, this, this. So let us see. So D lower bar epsilon s is less than D epsilon. Now that should be clear because
Clear from the objective function.
From the objective function, like if I take the lambda which optimizes D lower bar epsilon s, fix that threshold lambda. That threshold lambda will be feasible for D epsilon s, right? Because of the nature of the objective function. Okay, so maybe the optimizer for D epsilon s was some lambda prime strictly larger than lambda. We don't know. That's why we have this inequality. Then again, D epsilon s is less than D epsilon 0, which I remarked a short while ago, because here I'm optimizing over all possible subsets, whereas in D epsilon s, I fixed the choice of the subset. Okay, so this could only do better. So it's less than or equal to. And even this is trivial because here I'm looking at a hypothesis test. I'm looking at a vector m, which either takes a
Yeah.
zero
So if
value
the
or a one value.
optimizer, exactly, it's over a larger possible set of
It's over it's optimized over larger. So these are all trivial. The non-trivial part is the first inequality. Okay. So let us try to prove it. Let us call this left-hand side D epsilon minus delta min minus log 1 by delta as a quantity called lambda. Okay. And now let us consider this vector. So what is this vector? This vector, so I have the plus set. So basically these are the symbols x where the ratio px by qx is larger than 2 to the power lambda. I mean, lambda is this left-hand side. So this is the indicator vector for that set. So it is a vector which takes the value 1 for x's where the ratio is larger than 2 to the power lambda, and it takes the value 0 for x's where the ratio is smaller than 2 to the power lambda. This is the indicator. Now let n be the optimizing vector in the definition of this d mean epsilon minus delta quantity. Okay. So let's see. So what do we have? So look at this vector p minus 2 to the lambda q. Okay. So there are some positive guys, positive coordinates here, there are some negative coordinates out. Now what I'm doing is that I'm taking the dot product with this indicator vector. So basically I'm looking at the sum of the coordinates with positive values only. Right? So this is just a fancy of saying that look at the vector p minus 2 to the lambda q. So throw away the negative coordinates and now add up the values in the positive coordinate. That's what this is. So I claim that this is larger than m dot p minus 2 to the lambda. Okay. So this should be pretty clear because if I take a m, so what was m? M was a vector whose each coordinate is something between 0 and 1. So now if I put in positive values to the negative entries in p minus 2 to the lambda q, I'm just shooting myself in the foot. Okay. So if I really have to maximize this quantity, I should be putting 0 for the negative coordinates, and for the positive coordinates, I should put the maximum allowed, which is 1. So basically, I come down to this. So this is a trivial inequality. So now I'm just expanding it linear to the dot product. And now, because m is an optimizing vector in the definition of this, so m dot p is larger than 1 minus epsilon minus delta. Okay, from the definition of d min, right? The feasibility constant, 1 minus epsilon minus delta. And let us look at m dot q times 2 to the power lambda. Okay. Now, okay, so again, remember m is the optimizing vector. So m dot q is 2 to the minus this d min quantity, d min epsilon minus delta. So that is m dot q. And what is lambda? Lambda is this quantity. Okay. So if I multiply the two, I will get in the exponent minus log 1 by delta, which will become minus delta. Sorry, I have to answer the bell. I will just be back. Okay. So sorry about that. Okay. So now, okay. So what does this show? This shows that this threshold lambda is feasible for d lower bar epsilon s, right? So what is the feasibility condition here? It is just the sum of the coordinates of the vector p minus 2 to the lambda q on the positive part, which is just this quantity, okay, which is larger than 1 minus epsilon. So this is feasible, which completes the proof. That means this is less than d lower bar epsilon. Is this clear?
Yeah.
Yeah.
I mean,
okay. Yeah. Good. So let's go ahead. So, okay, so what we did here was we just showed that all these quantities are around d epsilon min. Remember, like finally we'll be working mostly with d epsilon min, but some proofs are easier with d epsilon s or d lower bar epsilon s. So it's useful to have these quantities, but they're all around d epsilon. Let's look at the other extreme. Okay. Yeah. So actually, I think this should satisfy your query a little bit more. That why in
Pranav, I just have a question. So, can you just go back to the previous theorem?
Okay.
Isn't this sandwiching implying continuity of d lower d bar epsilon d epsilon s?
Why? These are not the same, no? This is epsilon minus delta.
Oh, this is epsilon minus delta. Okay. Oh, yeah, right. Sorry.
Yeah. I mean, you do need that epsilon minus delta. So, yeah. Okay. So, d epsilon s is not continuous. D epsilon 0 is also not continuous. But all that is captured in this fudge.
But that also pretty much tells you that even though it is discontinuous, the discontinuity isn't very bad.
It isn't very bad. Yeah.
Okay.
True.
Okay.
It isn't very bad. So that is why, I mean, the maximum likelihood strategy was not so bad. it was not the optimal strategy, but it was not so bad. So that, I mean, that's another way to reconcile. Okay, any more comments about this? Okay, let's go to the next topic. So yeah, so this is in relation to question that Ishan asked. Why in the smoothing definition, like something is minimum, something is maximum. Okay, so remember the minimum was for smoothing the Renyi divergence d alpha for alpha bigger than 1. And I have remarked earlier that for alpha bigger than 1, d alpha behaves sort of like d max. So here is the formal proof of that. Okay, so the informal KQ is for alpha bigger than 1, d epsilon alpha is approximately d epsilon max. So the first part is we have already discussed before. This is the monotonicity of the Renyi divergence, the smooth Renyi divergence. This is trivial. The non-trivial part is the second inequality. And here you can really see where alpha bigger than 1 is coming. Okay, so for a moment, if you believe this inequality, then we had argued that to smooth d max, it makes sense to take minimization, and which further implies that to smooth d alpha for alpha bigger than 1, one should take minimization. Okay, and it also strengthens our philosophy that the two most important quantities to work with are the two ends of this Renyi divergence spectrum, the Dmax and D0 or Dmin, as we call it. Okay, and everything else behaves like one or the other. There is that exception of the D1 in the middle, which we will keep coming to from time to time. Okay, but other than D1, everything else is behaving either like Dmax or like Dmin. Okay, so for the second inequality, let's see. So, this is the smooth Renyi entropy of order alpha. So let us say I have this vector p prime less than or equal to p, and epsilon close to p in L1. Okay, such that which attains the optimum for the smoothing definition. So the smooth divergence for p with respect to q is exactly the non-smooth divergence of p prime with respect to q. So now let me define a subset of my sample space by the following definition. So S is the subset of those symbols X where the ratio P prime X by QX is larger than 2 to the right hand side. This is the right hand side. Okay. Then what can I say? So the equality here follows from the definition of Renyi divergence. Okay. So I just put the alpha minus 1 on the left hand side and exponentiate to remove the logarithm, and I get that. Okay, and I write the right hand side in this slightly fancy way for what's coming. Okay. And now I will only concentrate on those symbols X that are in the set S. So I get this greater than or equal to inequality, no big deal. And now what do I know for this set X? The ratio P prime X by QX is larger than 2 to the RHS. Okay, so I plug that in. So I plug that in, do the simplification, and I'll get this quantity. And what remains is just this part, which is the summation of P prime X for X belonging to the set. So this implies that summation P prime X for X in S is less than epsilon. So now define a new vector P double prime as follows. P double prime equals P prime if X does not lie in S, and P double prime is equal to 0 otherwise. So in other words, I just take P prime and I zero out the entries in the set S. Then what do I have? Then of course P double prime by QX is less than 2 to the right hand side for all X. Okay. And by triangle inequality, I can check that P double prime. By triangle inequality, I can check that P double prime is 2 epsilon close to P. Okay, and of course is also less than or equal to P, just obtain by zeroing things out. Okay, so I get this. So D max 2 epsilon is less than or equal to D max, the non-smooth D max for P double prime with respect to Q, which is less than the RHS. Okay, so this finishes the proof of this theorem. Any questions?
Oh, can you just repeat the reason for why taking the max made sense? I couldn't get that one.
Oh, so you have to first
You
argue
gave some
that
meta reason, right?
no, you have to take the min to smooth. No? So it makes sense if you want to smooth D max, it makes sense to take the min because D max is already a max, right? It's a maximum ratio Px by Qx. And this ratio can be unnaturally large because of some pathological excess. Okay. So you basically have to drop them out, and that's the drop them out or lower them. That is the P prime, which lowers them to the right amount. Okay, so if you have to smooth Dmax, the only sensible thing is to do min, and because D alpha behaves like Dmax for alpha larger than 1, it is sensible to do min for them. That's the full meta argument.
Okay.
Okay. Yeah. Any further questions? Yeah. Next. Okay. So now the other side, I said for alpha less than 1, D epsilon alpha looks roughly like D0. Okay. So D0, D min, they're all the same. So the take home is D epsilon alpha is approximate to D epsilon min for alpha less than 1. Formally, this is the statement. So let us see. Okay. So what we will show is the following. So okay, so we will show that this quantity is less than ds. So this is the information spectrum divergence, which is close to d0 and d min below. Okay, so it is less than this quantity. Now, then the next thing is it is further less than this, which is a trivial thing. Then further upper bound by d0, which is a trivial thing, then further upper bounded by d alpha again. So the second, third, and fourth inequalities are trivial. So this is trivial because I have so here the error parameter was 2 epsilon minus delta. Here the error parameter is larger. So if the error parameter is larger, then I can use a larger threshold. So let's come back to d epsilon. See, if I increase epsilon out here, if I increase the error parameter, then I can squeeze in more x's into the plus set out. Okay. So squeezing in more excess means the threshold can be correspondingly larger, right? So lambda is of course the largest px by qx in this plus set. So squeezing in more x naught means increasing lambda to lambda. Okay. So that is this monotonicity in this parameter. Then this one we have already seen that is the same to epsilon out here. So this prescribes a fixed subset. This optimizes over all subsets. So this is this part which you have already seen. That comes out here. And then the last inequality is the monotonicity of the smooth Renyi entropy. So I'm going from 0 to alpha. This only goes. So these are the easy parts. The non-trivial inequality is the first one. Any questions about this? Okay, so let's try to prove the first inequality. Okay, so again, it's a similar strategy to the previous proof. So this is a smooth alpha divergence for the smoothing parameter epsilon minus delta. So let it be the alpha divergence for p prime, where p prime is close to p and less than or equal to p. Again, define the set in a similar fashion. This is the set S of those symbols x such that the ratio p prime x by qx is less than 2 to the left hand side. Okay. Then again, we start. The first equality is the definition of the alpha Renyi divergence. Then I'm only keeping those x's in S. So this is greater than or equal to. Okay. Remember, these are all positive quantities. So this is what goes on. And then note that for x in S, this ratio is less than 2 to the LHS. So I plug that in, but now alpha is less than 1. So the exponent is negative. Okay. So this direction of the inequality is correct. And I end up with this quantity. Same as this. So this implies that summation p prime x for x in S is less than epsilon. Okay. So what does this tell us? So look at symbols x in S complement. So for those symbols x, p prime x by qx is larger than 2 to the LHS, right? This is S in S complement is larger than 2 to the LHS. And remember, p prime is less than or equal to q. So the ratio of p by q is even larger. So, okay. So what do I have for symbols x in the complement of S? The ratio is larger than 2 to the left hand side. And what is the probability under px? So the probability under px is larger than the probability under p prime x, right? Because p is larger than p prime, and the probability under p prime x by definition of the probability of the p prime x by the definition of d epsilon s is larger than 1 minus the smoothing parameter, which is 2 epsilon minus 2. Okay. Okay. So what have we concluded? Yeah, so we've concluded this, that this is larger than the left hand side. Okay, so this proves the first inequality out here. And now to get the statement in the theorem, what we will do is that we will go back to this out here. We have the connection between ds and d min out here. So we'll use the fact that ds is larger than d min with this fudge additive term, and it's smaller than d min without the fudge. Okay, and once you plug that in, we get the expression. So any questions about that? Okay. Okay, so let's go ahead. Yeah. Okay, so let us summarize. So the two most important quantities that we work with are d epsilon max and d epsilon min. And the moral of the story is d epsilon alpha is close to d epsilon min for alpha strictly less than 1. And d epsilon alpha is close to d epsilon max for alpha strictly bigger than 1. So really d1, which is the Shannon relative entropy, is special, and it's at the borderline. And usually we will not deal with a smoothed version of it. Okay. So that's for various reasons. So one reason is because really the borderline, like below it quantities tend to d epsilon min, above it quantities tend to d epsilon max. Okay. So also the smoothing is different for d epsilon min and d epsilon max, as we've argued. Okay. Then also the like if I go to the asymptotic IID limit, all this smooth Renyi divergence goes to D1. So in that sense, D1 is special. I mean, they go to the non-smooth D1. So the non-smooth D1 is special. Okay. Now let us see. We don't have time. So I wanted to give this an exercise, but I'll give the proof. So this is very simple. So this is okay. So we know that the two ends of the spectrum are d epsilon max and d epsilon min. So what is the connection between them? Okay. So this is given by this expression. So of course, yeah. So the moral of the story is d epsilon max is approximately d1 minus epsilon min. Okay. So there's some kind of a mirror image of each other. And okay, since we don't have time, the proof is very simple. So recall that d epsilon max is nothing but d lower bar s of 1 minus epsilon. And I know the connection between d lower bar s and d min. Again, d lower bar s is lower bounded by d min, upper bounded by d min. So I'm just using it out here. Okay. So d lower bar s is lower bound by d min, upper bound by d min. You plug that in, and this is what you get. Okay. And it is because of the connection of d under bar. Okay. we know that so we know that d under bar s of 1 minus epsilon is d epsilon of d epsilon max. So in a sense, if you are looking at the d under bar definition, I mean, it is one definition which continuously interpolates from one end of the Renyi spectrum to the other end of the Renyi spectrum. So that's the really the beauty of well, this was not Hahn's definition. So this is Leditsky and Datta's improvement of Hahn's definition. So the beauty of this definition is that as the error parameter epsilon goes from 0 to 1, you go from one end of the Renyi spectrum to the other. In any case, because we will still keep them separate, we will concentrate mostly on d epsilon min and d epsilon max. And it's because, as I said earlier, without defining things, that the d epsilon min controls the packing properties, d epsilon max controls the covering properties. So we will, I mean, keep them separate and concentrate on them the rest of the course. And we will also keep coming back to d1 because both these quantities approach d1 in the asymptotic ideal. So we will stop with this slide. So we've spent a lot of time studying Renyi divergences to get a nice picture of the two most important quantities, d epsilon min and d epsilon max. I mean, one could have defined them separately and proved properties about them, but I thought this will give a better idea of how they relate to each other and the fact that there are things which continuously interpolate between them. Okay, so the most useful Renyi divergences in the order of increasing alpha as follows. So d epsilon 0, which is almost the same as d epsilon min or d epsilon s or d under bar d epsilon s. So this controls the packing arguments. So example is the noisy channel coding, canonical example of a packing argument. So that is controlled by d epsilon 0. Then d half, the non-smooth. D half is important because it's minus 2 times the logarithm of the fidelity. And fidelity was a very useful notion of distinguishability of probability distribution. It will become even more important when you go to the quantum half of the course. Okay, so, but that is already captured by Renyi at d half. Then d1 is important. This is a good old Shannon relative entropy. We know a lot of information theory built around that. And very interestingly, this is the asymptotic IID limit per resource use of all the d epsilon alphas, including the two endpoints, d epsilon and d epsilon max. So the entire Renyi spectrum, after smoothing, goes to d in the asymptotic IID limit. So per resource use means you have to divide by n. If you're repeating your states n times independently, you have to divide it by n to get d. So this is d1, very important. The non-smooth d1 comes in the asymptotic IID limit of everything. Then d2 is also important. So it is important for its connection to transmission of quantum information, which we'll see in the second half of the course. Maybe, maybe not. Okay, but there's also a classical importance to it. So it has connections to collision probability. So what is the collision probability? It is the probability that two independent samples drawn from P are equal. Okay. So let us say I draw two independent samples from P. The probability that they're equal is this expression, summation x px square. So this is
only I'm left. Only I'm left.
Oh, you are left.
Yeah.
Okay, so we'll stop there. Yeah.
Okay.
Okay. So 2 to the, so this is equal to 2 to the minus h2, which of course we can express as 2 to the d2 minus log mod x. So here y is a singleton set. I mean, y is just introduced to define the conditional entropy. And finally, of course, d epsilon max is important because it controls the covering argument, example, noiseless source. Okay, so we will stop here and meet on Thursday, and hopefully like there'll be more than 2 of us.
Okay.
Yeah. Let's stop the recording.
No, I think a lot of people watch on YouTube because Gautam follows along on